Bismillahir Rahmanir Rahim. Assalamu alaikum wa rahmatullahi wa barakatuh. Hoping, dear students, you all will be doing fine. As you know that in the last two lectures, I covered the power flow method, that is called Newton-Raphson method, and then I even solved a problem using this particular method. So with those two lectures, now the part of this course related to power flow is ended, and now we will start with the next important part of this course related to the fault studies. So in a power system analysis course, I have mentioned this even before, that majorly we cover three parts. One is related to the power flow. The other part is related with the fault studies, and the next part, or the last part that we cover, is related to the stability analysis. So as I mentioned that we discuss the power flow quite in detail, and we have discussed two different methods of solving a power flow problem. In the beginning we discussed the general equations of the power flow, and we also discussed the different types of buses, the non-linearity the non-linear nature of the power flow problem. Even I demonstrated that to you with the help of in the lab I demonstrated that to you. And then we solved power flow problems using Gauss-Seidel method, and also I solved a problem using Newton-Raphson method. So we discussed the power flow and the different techniques. Majorly in this course I talked about two techniques. So we covered this part of the power system analysis course quite in detail, and I hope now with the help of the theory and tutorials or solving problems, you have now understood the first part, or the one of the important part of the power system analysis course. So with that we ended the power flow, our discussion on the power flow, and now we will start with the other important part of this course related to the fault studies. And in today's lecture I will cover the balanced faults, or let's say the related theory to the balanced faults, and then in the next lecture I will solve a problem to make the understanding or to make it more clear to you. So let's start with the second part of this course, that is related to the fault studies. So now why fault happens in a power system? So majorly there could be reasons like related to the insulation failure of the equipment, could be generator, transformer, circuit breaker, or even insulators, etc. So if the equipment insulation fails due to, for instance, these reasons, it may result in a fault. We know that in a transformer, oil basically, it acts as a cooling agent. Also it performs the function of insulation. So similarly in all equipments we have insulation, either in a solid form, or could be liquid insulators. Also we have gas insulation. So when the insulation fails, then it results in a fault. And insulation may fail due to system or voltages. For example, in the lightning, where we have very high voltages, it may lead to, if it fall, let's say on a line or on insulator or on an equipment, it may result in the failure of that equipment if it, let's say, damages the insulation. Similarly, there could be switching surges or could be overcurrents, because we know that with the overcurrents, heat is an associated effect, and that may result in the failure of the insulation, leading to the damage of the equipment. Similarly, insulation contamination. So majorly the fault appears, or the fault happens when there is a failure of insulation. So those insulation or solid insulators may fail due to these uh, occurrences. For example, system over voltages or overcurrents, or insulation may even fail due to the contamination, either in the insulator itself when there are, let's say, impurities. So then the strength of the insulator, it is weak. Or let's say, if in a transformer, if some tiny drops of water, let's say, if that mixes with the oil, so then the strength of the insulator does not remain, of a high level. And if such contamination take place in a solid insulator, whether it's a, let's say, gas, or it's a liquid, or it's a solid, so contamination may also result in the failure of the insulation. There could also be other reasons, for example, mechanical uh, forces or mechanical causes. So it may also, let's say, if the insulators are stressed mechanically, so it may also lead to the failure of the insulation. And all these failures of insulation, whether it is due to the over voltages, or it is due to the heat related with the over currents, or related with the addition of the impurity, or for instance on the line insulators, if, let's say, dust accumulate, or some other sort of, let's say, impurities, or let's say, for instance, some impurities from the industries, let's say, if it sit on the surface of the insulators, so the strength of the insulator does not remain of high level, and it then, even under the normal condition, or under the operating voltages, if, let's say, the strength of the insulation or that of the solid insulator decreases, so then the voltages, even the normal voltages, because the strength of the insulation decreases, so it may lead to, let's say, uh, it may lead to the fault in the power system. So majorly due to the insulation failure, fault may take place. Also, the broken of the phase conductors, if phase conductor broke, so it may also lead to the fault. Tree enters, let's say, safety corridor of transmission or distribution line. So even these are the other reasons of the a fault in a power system. And I hope you remember that even we discussed this point, that fault is not only related to these, let's say, reasons. Fault is a condition where the parameters or the quantities in the power system, it exceed the allowable limit. So that is basically a fault. Fault is not only short circuits. It's also, whenever the parameters, let's say, either frequency or voltage or current, if it exceed the allowable limits, then those conditions are sort of characterized, or sort of said as a faulty condition. So we have now discussed these reasons, and let me even show you some pictures, that in the case of the lightning, when it falls, let's say, on a building, or on a live wire, so it may result in the fault, because these are over voltages, and I mean quite high voltages these are. We will discuss that. I mean the concept of the lightning, or the yeah, the concept of the lightning will be discussed in the course on high voltage engineering. So these basically involve quite high voltages, and if it fault on a building or on a power system equipment, so it may lead to the damage of the insulation or the damage of the equipment itself. Similarly, you know, or you are familiar with this kind of situations where even a bird, if it, let's say, sitting on a grounded wire, if it also touches the live wire, so it may also lead to the faulty condition, or it may lead to the fault in the power system. Similarly, when the tree fall on the live wire, so maybe even the live wire gets broken, or maybe it is let's say I mean the sag may be more, or it may be, maybe even it pushes the conductor to quite close to the ground. So all these can take place. So even with the trees, when it fall on a live wire, it may also result in a faulty condition. Similarly, there are also other pictures, you see. I mean, many different pictures are shown here to to let's say illustrate that due to all these different I mean reasons, fault may take place in a power system. So fault, as I mentioned, it is not only short circuits, it is not only the let's say the appearance of over voltages in a power system. Fault in a general is when the parameters exceed the allowable limit, and you know that parameters could be frequency, could be current, could be voltage. So whenever these parameters exceed the allowable limit, or the standard, let's say, operating limits, so then it is characterized as a fault, obviously depending on whether the fault is of severe type, or it is of a, let's say, I mean within the limits, when some actions are taken and then the system is restored. So but anyhow, fault is when the system parameters are no more in a allowable limit. So now let's proceed, and we have different types of faults in a power system. The fault could be what we call the balance fault, or a symmetrical fault, or it could be unbalanced or unsymmetrical fault. So when all the three phases are involved, either touches, I mean when there is a, let's say, when the three lines touches each other, or when they are connected through even the ground, so these result in a balanced type of fault, because all the three phases are equally affected. So that's why when all the three phases are equally affected, so then the system will still remain balanced. So in a balanced system, when a three-phase fault appear, either the lines touches each other or they are connected through the ground, so then these two conditions result in a balance type of fault, because all the three phases are equally affected. And these faults, later on we will discuss that these types of faults, or the studies of these types of faults, are carried because the system still remain balanced. So that's why the studies are conducted using per phase analysis, because you know that in a balanced system we don't need to solve all the three phases. Just one phase or per phase analysis would be more than enough to conduct the studies under the faulty condition, because in these two conditions the system will still remain balanced. As I mentioned, all the three phases are equally affected. But in these cases where either two phase fault occurs when the two lines touches each other, or when they are connected through the ground, or even when one phase is connected to the ground, so these conditions or these three types of faults are categorized as unbalanced faults. So faults could be either balanced, faults, balanced faults, or could be unbalanced faults. So these two are categorized as balanced faults, while these three, the schematics which are shown in, I mean, these three conditions or these three scenarios will result in a unbalanced fault. So unbalanced faults. So these three are unbalanced faults, and these are balanced faults, because I mentioned that all the three phases are equally affected. So in this case, only one or only I mean the analysis of a single phase will be conducted. But here we will discuss later on. So this lecture is I mean in this lecture we will majorly talk about the balanced fault analysis. Theoretically we will discuss it in this lecture, and then in the next lecture I will solve a problem to make it more clear to you how to conduct the analysis when we have a balanced type of fault. So these are basically the different types of faults. Also, if I hope you remember that we discussed that in a short circuit type of fault where there are overcurrents. We have discussed this figure even before in the course when we were discussing the fuses. So I hope you remember even this figure where short circuit currents are shown. And I even discussed at that time that during the short circuits, we have three different regions. The first region where the current magnitude is quite high, that region is characterized as, so this region majorly this region is characterized as subtransient period, or it is called as subtransient period, where the magnitude of the current is quite high. Afterwards, then we have a transient period. So the next period, or the next pole, I mean the next, because the magnitude of the current, it decreases or it varies during the short circuit condition. So the next period, or in the next period, we have then what we called the, so this is the transient period. So this is the transient period, and in the beginning where the magnitude of the current is quite high, this is characterized as subtransient period. And then afterwards we have, let's say, the steady state characteristics where the current I mean is within the allowable limit. So this is basically the steady state. If you want to look here, there is a, I mean a dotted or dashed line is drawn here where touching the peaks of the current under steady state condition. And if when the, as I mentioned, that fault is fault refers to any condition where the parameters of interest or the quantities in a system when it exceed the allowable limit. So as one can see here, when the current exceed the permissible limits, it is characterized as a fault. Doesn't matter whether the current magnitude lie in the transient portion or in the subtransient portion. Similar is the case whether it is a frequency or it is a voltage. So whenever the parameters of the system or the quantity in a system exceed the allowable limit, so those conditions are termed as a faulty condition, and then appropriate action must have to be taken to restore the system. Otherwise, if let's say these currents or if let's say even the case of the over voltages or that of the frequency when it let's say exceed the limits, so if those conditions are allowed to persist, then it may damage the system, or it may even result in, I mean in a, what we call basically, if the conditions are worst, then it may lead even to what we call the blackout. So let's say if we restrict our discussion only to the short circuit currents, so if the short circuit currents are allowed to persist, so then what can happen? Because the magnitude of the current, as I mentioned, could be even several orders of magnitude larger than the normal operating currents. So if these currents are allowed to flow in the power system, it may lead to thermal damage, because with the high currents, heat is associated, and that may lead to the thermal damage to the equipment. Also, you now even when I mentioned that it could lead even to the mechanical, let's say, it could even lead to the because the insulation can fail even due to the mechanical causes. And if one look here, the if such high current is allowed to persist, it may cause mechanical damage due to high magnetic forces during fault, because we know that the force is related with the current. If I remember correctly, it is the force is associated with the what we call the magnetic flux density, if I remember correctly. What we all this is basically called B field. So, but anyhow, it is the magnetic flux density. This is the current magnitude, and that is the length of the conductor, let's say. So, if these high currents, or the high currents of, I mean, if they are allowed to persist, it may lead to the it may lead to strong forces in the power system. And if, let's say, such strong forces act on two, let's say, live conductors, if they are pulled apart with such high forces, it may obviously lead to the damage of even the conductors. So it may damage the windings, and let's say, in a transformer, or could be in a generator, or it can even lead to the damage of the bus bars, because high forces are exerted on the bus bars or even on the live conductors. So if they are pulled apart, or if, so with such high force, so they may be broken. So that's why it may either lead to the thermal damage or even to the mechanical damage. So it is important to remove the faulted section of the power system from service as soon as possible. Otherwise, it will lead to the damage of the system, or even of the components of the power system. For instance, transformer or generator, or live wires, or bus bars, or some other parts of the power system. So it's important to remove the faulty part from the power system. And for that we have different apparatuses to detect the fault and to operate before causing any damage to the system. We have discussed some power system protection techniques, for instance, with the help of fuses and then circuit breakers, and then some other uh, effective protection schemes. The faulty portion of the power system can be removed in order to restore the system, or to avoid damage of the equipment. So we have discussed different protection schemes. So it could be circuit breakers, SF6, which is one of the uh, type of circuit breaker, having the SF6 gas as a medium for quenching, let's say, the arc. Because in a breaker, I don't know if you have studied it in detail, or you maybe in a power system protection course you will probably study it in detail. But during the faulty condition, the contacts of the circuit breakers, they are I mean pulled apart, and during that period there basically appears an arc on the contacts of the breaker. So when such a when the contacts are pulled apart, there appears an arc. And if that arc, let's say, is not, because arc, it is current, which is associated with very high amount of heat, because it is the flow of the current in that medium. So it is important to quench the arc as soon as possible, and SF6 is a medium for quenching that arc. So these are basically, I mean, one of the type of the breakers are SF6 circuit breakers. And we have also high speed distance protection for transmission lines. So I hope you will study this protection more in detail in the course on power system protections. And the clearing time of such type of fault using these types of schemes could be from 80 to 100 millisecond, because the effective or the efficient the protection scheme is, the more is the or the efficient the protection scheme is, the less will be the damage to the equipment of the system. So it is important to clear the fault as soon as possible. So we need basically the protection scheme in order to avoid the and in order to avoid the damage to the system, whether it's thermal type or it's mechanical type. But even the designing of the protection scheme, for designing, let's say, the or for determining the rating of, let's say, the circuit breakers or that of the other schemes, we need to conduct some studies, because we need to know the amount of the quantity of the current or the voltages on different buses during the faulty condition, in order to design the appropriate protection scheme that may become let's say effective, or that will play its role during the faulty condition. So such studies need to be conducted before designing the protection scheme, before installing the protection devices in the system. So we need to know the bus voltages, also the current that are flowing in the power system during faulty condition. And I mentioned that fault could be of different types. It could be balanced fault, it could be unbalanced fault. So we need to carry the analysis under each of these conditions to know the currents and also the voltages during such type of faults for designing the protection scheme. So now let's proceed. So we need to carry the fault studies, or we need to carry the short circuit studies in order to determine the bus voltages and the line current during these different types of faults. It could be three-phase balance fault, as I mentioned, because the system still remain in balanced condition, and these kind of studies will be conducted only using one phase. So these types of faults are rare, but they are one of the most severe type. Although their occurrence frequency, let's say, is quite small, 5% of the cases, of the total cases, are characterized as, 5% of the total cases are where balanced fault occurs, but they are of the most severe type. And the unbalanced fault could be single line to ground fault, could be line to line, could be line to ground fault. So they occur more frequently, especially of this type, single line to ground fault, where the frequency, or let's say the percentage, is quite high. But the most severe type is this one. So we need to know the voltages and current during these faults in order to determine the rating of the protection devices, or to design the protection scheme. So why fault studies? Even I mentioned, because fuse, if you remember, we discussed that it detect and it operate individually, because it detect the current and then it operate to remove the faulty section. But it is actually not that effective protection scheme. For expensive equipment, we then use more sophisticated, or we use more sophisticated protection devices, for instance circuit breakers. But circuit breaker does not work alone. There is another equipment what we call relay, because circuit breaker only operate, or it when the contacts of the circuit breaker they are pulled apart, then it remove the, or it clear the fault. But the detection of the fault take place uh, with the help of the relay. So relay detect the fault and it is connected with the circuit breaker. You know that we have carried this discussion even in the course on power distribution and utilization. So the relay detect the fault, and then it send a signal to the circuit breaker to trip or to operate, so that to remove the fault or to clear the fault. So we need to carry the fault studies for determining the relay setting and also the coordination. And also the fault studies we need to carry for selecting rating of protective switch gears, because we need to know the current under the worst condition to determine the ratings of the protective equipment, could be switch gear, because with that we will know the size of the equipment or protection devices, so that it may clear the fault without being damaged. So we need even to know the ratings, because it cost, in any case it cost. So we could make the size of the protection devices quite large, but that will cost more. So we need to somehow find an optimal solution for protecting the system, and at the same time reducing the cost of the protection devices. So we need even to know the rating of the protective switch gear, so that to clear the fault without being damaged. And we know the also the fault studies for determining the relay setting could be, as I mentioned, there could be three phase balance fault. So we need to know the phase relays, and could be unbalanced faults. So we need to select and set the ground relays. So we need the fault studies, or we need to conduct the fault studies in order to determine the relay setting. Could be phase relays, or could be ground relays, depending on the type of the fault. And we also need to know the rating of the protective equipment in order to uh, make the cost of the total protection scheme low, and at the same time providing safety to the system. So that's why we need to carry the fault studies. Now as I mentioned that the balanced fault, because in this lecture we will mostly talk about the balanced fault, and then the other types of faults we will discuss in the next lectures. So in this lecture we will mostly talk about the balanced three phase faults. And as I mentioned that it occurs infrequently. The total cases, or the total percentage of the cases when the balance fault occurs, it is quite rare, or the percentage is quite low. But it is the most severe type, because the current flow during the balance type of fault is quite high. The current is quite high. So this is the most severe type. And as I mentioned, network is balanced because all the three phases they are equally affected. So the system will still remain balanced, and we will conduct the studies only using one phase. So solving using per phase basis. So just one phase will be solved. Now let's talk about the synchronous generator reactance, because as I mentioned that during the short circuit type of fault, the current profile, it have a subtransient period where the current magnitude is quite high, several orders of magnitude higher than the normal operating current. Then we have a transient period, and then we have a steady state period. So correspondingly we have different reactances of the synchronous generator. So the reactance that we have, or the reactance that correspond to the subtransient portion of the current, is known as subtransient reactance. And as the portion of the period where the current magnitude exists in the subtransient portion is quite small, so that's why subtransient reactance, it occurs or it appears for the first few cycles of the short circuit current. So the reactance that correspond to the subtransient portion of the current is known as subtransient reactance. And similarly, we have a transient reactance, and then we have a steady state reactance. So likewise, we have during the short circuit period, we have subtransient current, then we have a transient current, and then we have steady state current. Correspondingly, we have a subtransient reactance, then we have transient reactance, and then we have steady state reactance. So it means that if one look to deeply to these different concepts, or the different, let's say, representation of the reactance, so it means that as the current during the faulty condition vary with time, so it means correspondingly the reactance will also vary with the time. And that discussion, let's carry this discussion. So as I mentioned, since the three reactances, they correspond to the three different portions of the short circuit current profile during the faulty condition. So X, which represent the reactance, it varies with time under short circuit condition because the current also varies. So now let me explain this concept to you, although it is not that simple. I will try to make it as simple as possible, but remember that this is not a simple concept. But anyhow, let me try to make it as clear or as simple as possible to you. As we know that the reactance, is equal to, or inductive reactance, it is equal to omega L. Now if we further look to the inductance, we know that inductance is equal to flux linkage per unit current, or divided by the current. So I will deliver this concept. I will talk about this concept, although I mentioned it is not a simple concept. But anyhow, to make it clear to you, I think even I will carry a small discussion. But if one look to the current during the subtransient reactance, as I mentioned, it is several orders of magnitude higher than the normal operating current, and correspondingly the current magnitude is higher during the transient period, and then we have steady state condition. So the current magnitude is highest during the subtransient period, then we have the current magnitude in the transient period, and then we have in the steady state period. So now if one look to this particular expression, we know inductance is related with the flux linkage divided by the current. So during the subtransient period, the current magnitude is the highest, and then if the current magnitude is highest, then it means that inductance during that portion will be smaller, because the flux that is caused by this high magnitude of current, it does not get linked. I'm talking about the flux. It does not get linked with the winding. As I mentioned, this concept is not that simple. So for you, it is more than enough to understand that during the subtransient period, the current magnitude is the highest, and the flux linkage is not the same corresponding to the magnitude of the current. So even if we restrict the discussion to the profile of the current, saying that in the sub-transient period the current is the highest and correspondingly the inductance will be the smallest. So that's why when that inductance is multiplied with omega, XL is the resultant value. And as I mentioned that in the transient period the current magnitude will get lower, although it will be still more than the steady state period, but then let's say taking the steady state period as a reference, then the current magnitude in the transient portion will still be larger. So correspondingly we have this, let's say, inequality condition where the subtransient reactance, knowing that the current is the highest, will lead to the low inductance. So then the subtransient reactance is the smallest. Afterwards we have the transient reactance, and then it is the reactance under the steady state condition. So I believe, as I mentioned, this concept is not that simple, but that discussion will be more than enough for you, that during the subtransient reactance the current is the highest, leading to the smallest inductance and correspondingly the reactance. So the reactance is the smallest during the subtransient period, then it is in the transient period, and then we have the steady state reactance. So X varies with time under short circuit condition, and duration of short circuit current depend on the speed of protection. Obviously, as I mentioned that the protection scheme should be effective enough to clear the fault as soon as possible. But anyhow, it takes some time. So the smaller is the time, or the smaller is the clearing time, the better is the protection scheme. So in generally, we need to select X accordingly, because if you remember, I mentioned that during the fault studies, we need to carry the fault studies in order to determine the ratings of the protective equipment as well as the setting of the relay. So X is selected accordingly. The subtransient reactance, which is represented as X over 2 commas or whatever you call it. So it is represented with this notation. It is used to determine the interrupting capacity of the circuit breakers, because I mentioned that the reactance that correspond to the subtransient period of the current, where the current magnitude is the highest, meaning to say that under this portion or during this period the current magnitude is highest, the associated heat will be higher, and at the same time the forces that are associated with this magnitude of current will also be higher. So this period or the subtransient reactance corresponding to this period will determine the interrupting capacity of the circuit breakers. Interrupting capacity, or what we call the breaking capacity, is that capacity of the breakers which, or it is the rating of the circuit breakers representing the situation, or it basically determines that the circuit breakers will clear the fault without being damaged. So this capacity is known as the interrupting capacity or the breaking capacity, meaning to say that rating will indicate that even if such amount of current flows, so it will not damage the circuit breakers. So this is basically the interrupting capacity, or what we call the breaking capacity. So this is the interrupting capacity, and then it is determined by the subtransient reactance, and the transient reactance, it determines the relay setting. So obviously the current under this condition, in the transient condition, is less compared to the subtransient reactance. So the subtransient reactance will determine the interrupting capacity, of the circuit breakers, because as I mentioned, we can make even the circuit breaker larger, but then it will cost more, as the rating is related with the size. But I mean, then obviously the cost is another factor. So we have to reduce the cost at this, and at the same time we have to make the protection scheme effective enough. So this subtransient reactance corresponding to the highest current, it will determine the interrupting capacity, and then the transient reactance, it will determine the relay setting and coordination. So when the relay basically determine, or it detect that period where we have the transient current or correspondingly the transient reactance, so then it will detect that condition, it will send a signal to the circuit breaker, and then the circuit breaker will open its contacts to clear the fault. So we need basically the relay setting as well, because the relay, it detect the fault, and then it send a signal to the circuit breaker to clear the fault. So X, this prime D, which is what we call transient reactance, will be used for determining the relay setting and coordination. Also used in the transient stability study, as I mentioned that in the power system analysis course, the last part or the other important part that we will discuss later on is related to the stability analysis. So that will also be used, the transient reactance will also be used in the transient stability study. Now, fault impedance, as I mentioned, that we will in this lecture talk mostly about the balance fault. So another important parameter that are associated with the faults is known as fault impedance. And fault often involves impedance of itself. For example, arc resistance, because arc is the flow of the current, let's say in the gaseous medium or in the air. So air have some, let's say, resistance. So even there is some resistance offered to the arc, and that's what we call basically the fault impedance. But in the case when the fault impedance is, let's say, 0, then we termed it as bolted fault. So that is bolted, or what we call solid fault. So under that condition, then the ZF, which is the impedance of the fault itself, that will be considered as 0. If there is some ZF, obviously we will conduct the analysis, then taking that quantity into account. So now we will now talk about the theory, how to determine, let's say, the voltages or the currents during the fault. So we need to carry the fault studies in order to determine the bus voltages and the line currents. And we are at the moment, or in this lecture, talking about the balance faults. So we need to carry the balanced fault analysis in order to determine the currents that will flow during the three-phase balance fault, and also we will determine the voltages in the system when three-phase fault appear. How to calculate the current, the faulty current, when balanced three-phase fault appears. So for that we will use the Thevenin theorem. And what this theorem states, it states that the changes in a network voltages caused by an added branch, because when the fault appears, it will even involve an impedance of itself. So it means where the fault take place, an added branch, there will be an addition of the branch at that particular node. So changes in network caused by an added branch, what we call fault impedance, at a node is equivalent to those caused by the added voltage source, what we call the Thevenin source, and we will find it what we call basically pre-fault voltage. And for that we need to carry the power flow studies, because before the fault, or what we call pre-fault voltage, that is determined in any network at a particular node or at a particular bus using the power flow studies. So the Thevenin theorem will be determined, And what it says that this theorem states that changes in the network voltages caused by an added branch, what we call fault impedance, at a particular node is equivalent to those caused by an added voltage source, what we call pre-fault voltage, at that node with all other voltage sources shorted. So if you want to determine the changes which is caused by an added branch, what we call the fault impedance, it will be equivalent to those caused by an added voltage source at that particular node, what we call Thevenin theorem. So we need to determine it, and that is determined by using or by carrying fault power flow studies. So we will determine that source, and then the changes will be determined in the network with all voltage sources shorted. So let me now explain this theorem to you with the help of the circuits, or with some, let's say, figures. So let's say there is a network. This is the network, what we call the active network. This is the active network, and let's say that is the point, or that is the node at the power system where the fault takes place, and that is the fault impedance. So whenever there will be a fault, let's say, it will close, and then it will be the short circuit through the fault impedance. If it is bolted type fault, obviously this will be zero. But anyhow, fault usually involve resistance or impedance of itself. So let's say that is the network, the active network, and the faulty node, let's say, where the fault takes place. And remember, once again, we are talking about the balance fault. So in the balance fault, this is because all the three phases are equally affected. So only one analysis of one phase will be enough for determining the parameters of the interest. Now, this is the short circuit fault through a fault impedance. So this circuit, it represents the short circuit fault through a fault impedance by switch closure at this point. And this one represent, if one look here, the fault current is zero. It means that this circuit is the one which is the initial network condition before short circuit fault, because the fault current is zero. And we need to, as I mentioned, that we need to find this voltage, what we called basically the pre-fault voltage. So this will be determined at this particular node using or carrying the power flow studies. So that is basically the current is zero, which means that still the fault has not taken place, although it is shown here, but the fault current is zero, and that is the pre-fault voltage, pre-fault voltage. That is the pre-fault voltage, and we will determine it using the power flow studies. So now this is the initial network condition before short circuit fault, and when short circuit appears, it means that the voltage from this point to this point, because this is the fault impedance. So when it is shorted, it means the voltage should be close to zero. So now if one look here, these two voltages are of the same magnitude, and it means that the potential difference will be zero. So then if point F will be connected to the positive terminal of the let's say what we call the impedance, because we are talking about at this point about the positive cycle. So this is basically by these two opposing voltage source we represent the short circuit. So short circuit representation by two opposing voltage sources. And as I mentioned that according to this theorem, what it states that when a fault appears which will involve this impedance, so obviously it will cause a change in the network voltages, also in the current. So this change in this network in the voltages as well as in the current will be determined equivalently by adding a source with all other sources are shorted. So now this is the pre-fault voltage. We will find it using the pre-fault studies, and then with the help of the two opposing sources, it represents the short circuit, And this is basically, then we take only this one because it supports the direction of the current during the faulty condition. So then, and as this theorem states that with all other voltage sources shorted, so the changes that are caused by this added branch will be equal to the case where we have a Thevenin equivalent voltage with all other sources are shorted, and then the resultant will be determined by the addition of this one because this is under the faulty condition and this case. So the addition, I mean the before the fault, so adding this branch or adding the voltages and the current with the pre-fault condition will be the changes in the network voltages and current. So we will determine it under this condition, what we call Thevenin equivalent network. Then we will add those quantities with the pre-fault quantities to get the resultant quantities. But anyhow, it is always better to learn the method by working on exercises. So let me summarize these circuits. That in the beginning we need to find the pre-fault bus voltages using the power flow analysis, and you know that how to find a bus voltage using the power flow studies. Then the faulted network is reduced into a Thevenin equivalent circuit viewed from the faulted bus. Applying Thevenin theorem, changes in the bus voltages are determined and correspondingly the changes in the currents are determined. And bus voltage during fault are obtained by superposition of the pre-fault bus voltages and the changes in the bus voltages computed in the step when we consider only the Thevenin source and with all other sources are shorted. The current during the fault may now be obtained in all branches of the faulted system. But anyhow, to get a better idea or to learn this method, that what we call the Thevenin theorem of finding basically or analyzing a balanced fault. So we use the Thevenin theorem, and these are basically the this is the demonstration with the help of these circuits, and then I summarized it on all these steps. So let me now conclude the lecture. In the beginning of this lecture, we talked about the faults. We started the discussion about the faults because I mentioned that the other important part of this course is related with the fault studies, and we will discuss both balanced and unbalanced parts. So in this lecture we talked about the balanced faults, and then I even mentioned that during the balanced fault the system is balanced because all the three phases are equally affected. And also I discussed that we need to carry the studies of the during the faults, because if the faults are allowed to persist, it may damage the system. Even it may damage the equipment in the power system. So we need to carry the studies during the faults in order to determine the settings of the relays as well as those of the ratings of the protective equipment. So we need to carry the fault studies in order to determine the setting of the relays as well as the ratings of the protective equipment. And I mentioned that in this lecture we are mostly discussing the balanced type of fault. So balanced type of fault will be analyzed using Thevenin theorem, and then I demonstrated with the help of these different networks, and then I summarized all those steps. So we have now theoretically talked about the balanced faults, and we have even talked about the Thevenin theorem that will be used for determining the changes in the network when a balance type of fault appears. So with that, I now conclude this lecture. In the next lecture, I will solve a problem to make all these steps more clear to you. So see you inshallah in the next recorded lecture. Thank you very much for your attention. Assalamu alaikum wa rahmatullahi wa barakatuhu.